Recording stopped. Recording in progress.
Good morning. Sorry for the delay. I had to change the computer because there's a problem with the machine. We discussed about the coefficient of localization last time in spatial statistics lecture. And today we will be looking at some other measures related to the coefficient of localization. One is Lorentz curve. Did we discuss about the Lorentz curve before? Yes or no?
No, sir.
No, sir, no. So, from the coefficient of localization, we look at what it requires. We look at the 4 areas. We look at the manufacturing sector employment from the total employment. So, total employment percentage is 15 for the area A, manufacturing employment 5%. So, difference is minus 10. Second area 70 and 50, it is plus 20. Third area C 15 20 minus 5, and D 10 15 minus 5. So altogether minus 20 and plus 20. We take only one side, so plus or minus, and then get the absolute value. So coefficient of localization for manufacturing is 20 divided by 100, that is 0.2. And if you look at the same thing for services, 10 divided by 100, it is 0.1. So we look at the coefficient of localization calculation, requires the aerial percentage, both the activity and the base to add to 100. So it should be out of 100. And coefficient of localization, range of the values is 0 to 1. Whereas the location quotient, earlier we looked at a lower limit of 0 and upper limit approaching infinity. So if the coefficient of localization is 0, the percentage distribution of activity is evenly spread over the region in exact accordance with the base. So the only numerical way this can happen is if the aerial percentages for the activity are exactly equal to the aerial percentages for the base. Now, if you look at this coefficient of localization, if you have a map of, say, DS divisions in Sri Lanka with some parameter, you can calculate and plot a map showing how the coefficient of localization varies in different DS divisions, right? If you have a DS division map, and suppose you have the employment values of each of the DS division, and according to the population, what is the share you should receive for the employment, then you can calculate if you look at it as a percentage, so you can have plus or minus number and then add up together, so you'll find the coefficient localization for each region. Now, if you go into this Lorentz curve, which is another way to index the distribution of a variable among spatial units. So this is a graphical, sorry? Can you hear me?
Yes, sir. I'm here.
Right. Graphical display of the degree of inequality. It's a graphical display. So it compares the real distribution of some activity to some base distribution, and it's most commonly used to measure extent of inequality among a spatial unit, non-spatial units, but spatial units also you can use. If you look at this example, calculation of Lorentz curve, we take the same example, A, B, C, D areas, where manufacturing sector employment percentage is 70, 15, 10, and 5. So what we do is we order the areas from highest to lowest. Highest to lowest. So 70% is highest, 15, 10, and 5. So it makes 100. So total employment in these areas, you don't need to arrange it in that order, but it automatically comes. So 50, 20, 15, and 15. And then what you do is you take the cumulative value of each column, manufacturing employment percentage, cumulative value, you get 70, 85, 95, and 100. Cumulative total of employment, 50, 70, 85, and 100. So then what you do is you plot cumulative percentage of manufacturing employment versus cumulative total employment percentage. So if you look at this graph, you can plot, sorry, my missing graph is missing. And if you plot this Lorentz curve against the cumulative total employment versus cumulative manufacturing employment, and if the activity is evenly distributed across the areas of the region, the Lorentz curve is a straight line following the 45-degree diagonal. So if you plot it, there's an example here. You can see if you plot it, it should be a straight line. But because of inequality, you won't get a straight line, you get a line below that. So the deviation from the straight line shows the amount of inequality. So the straight line is called line of perfect equality. Line of perfect equality. Lorentz curve is based on the, so if you order it, say for example, from the lowest to highest, if you can put it on the other way also, highest to lowest, you can put, then you will see the other side of the graph. But if you order it here from lowest to highest, then you see the lowest is 10, and the cumulative income share is 20. So it is below the line. Likewise, if you plot it, you get the Lorentz curve, which is deviated from the perfect line of equality. So this is an example. I think I have deleted that slide. I had a graph line for this one. So this one also, we can put so if you plot it here, 70, 50, 85, 70, 95, 85. So if you plot a graph taking cumulative manufacturing employment on the x-axis and the cumulative total employment of the y-axis, you still get the Lorentz curve. You can do it in both ways. The lower one, out of this lower one, you should take it to the y-axis. So that's, now here you have the quintiles. It's actually not quintiles, five. There are 5. Lowest fifth, second fifth, third fifth, fourth fifth, and highest fifth. If it's a quintile, it is lowest fourth, second fourth, third fourth, and fourth. So here it is the lowest fifth. Income share is 10%, and cumulative income share is 10%. Second fifth, 15, cumulative is 25. Third one is 20, so cumulative one is 45. Fourth is 25, that comes to 70, and finally 100. So cumulative percentage of households, when it is 20, that is out of 100, 150 is 20, 20 versus 10. So it is below the line, right? So what you have in the graph table is the income, cumulative percentage of households, like out of 100, first 20%, second 20%, third 20%. So it goes 20, 20, 20, 20. So if you look at this graph, first 20, so if you look at this first 20, value is 10. Second 20, cumulative is 40 of the household, value is 25. Third cumulative block is 40 plus 20 is 60, you get 45. And next block is 80, you get 70, and 100, you have the 100. So it deviates from the line of perfect equality, and there is a kind of a gap between the perfect equality versus what you find here. So the highest gap, you can see it from here. So highest gap is 45 and 60. 25 and 40 also, you have a same level gap. So the data were used, the data in A table used to derive the Lorenz curve. The Lorenz curve shows the cumulative percentage of income earned by the cumulative percentage of households. If all households receive the same percentage of total income, the Lorenz curve would be the perfect income equality, that is the straight line. Line passes through F and E. The bowed Lorenz curve, it's bended bowed, shows an unequal distribution of income. The more bowed the Lorenz curve is, more deviated from the Lorenz curve from the perfect line of equality, more unequal the distribution of income. So this is another kind of assessment of the difference of the actual share and what you received as the right. The next one, from the Lorenz curve, we can calculate the Gini coefficient. Gini coefficient defined graphically as the maximum vertical deviation between the Lorenz curve and the perfect line of equality. So if you go back to this maximum vertical difference, this is the difference. So if you look at it, this is the difference. Here it is small. Here it is also not more or less same, but here it is small. So highest vertical difference between the two lines is the Gini coefficient value. So the range of Gini coefficient ranges from 0 to 100. Now, if you look at the coefficient of localization, which ranges from 0 to 1. The location quotient, it goes from 0 to infinity. It goes from 0 to infinity. And if you look at the Gini coefficient, it is scaled to 0 to 100. Why we range things to 0 to 100? Because it is easier for us to understand. When you say in the scale of 0 to 150, you know it's in the middle. right? 60, you know where it stands. But if you give you a scale from 25 to 918, and if I say 400 is the value, you don't know where it is. So that's why we have a range which we can comprehend easily as the range applicable to us. So it is 0 to 100. That's why we give marks also 0 to 100. If you do exam, you get the marks between 0 to 100. Because it's easy for anybody to understand. I got 40 marks means you are just below the middle value. So you can immediately understand it. The Gini coefficient is determined by identifying the largest difference between the cumulative percentages of the activity and the base. So you basically look at the largest difference between the cumulative value. You can do it from the table also. If you go to the table, if you look at the first one, 10, and your cumulative value is 20. Cumulative value is 10 for the income. Cumulative value for the household is 20 because 100 divided into 5 quintiles. So 20 difference is 10. Second one, your cumulative income share is 25. Your cumulative household share is 40. Right? So 40 minus 25 is 15. Right? Third one, 45, your cumulative share is 60. 60 minus 45 is 15 again. So that so far 15 is the highest. Next one, 70, your cumulative household share is 80. Difference is 10. So the highest difference is between 45 to 60 and 25 to 40, which is 15. So your Gini coefficient is 15 in this particular case. So largest value could be 100 and the smallest value, when there's no difference, is 0. That is how it goes. Smaller values of Gini coefficient and coefficient of localization indicate similarity between the areal distribution of the base and the activity. So if the values are small, it shows very close equality between these two. If coefficient of localization or Gini coefficient increases, similarity between the base and the activity decreases. Similarity decreases. The Lorentz curve and Gini coefficient can be used to measure the degree of similarity of the percentage distributions of any two activities, neither of which is necessarily based. So you can compare totally two different activities and see how similar they are. Okay, so you can compare non-related variables also. So 100 means Gini coefficient straight line. Then you have actual Lorentz curve. So if you look at the maximum difference between these two, you can get the Gini coefficient. So Gini coefficient is equal to the area between line of perfect income equality and the actual Lorentz curve divided by the entire triangular R under the line of perfect income equality. So what it means is, now if you look at this, what you get is the highest deviation, vertical difference between the perfect income equality and the Lorentz curve is the value of Gini coefficient. you can get it in another way. If you get the blue area, divide by the area of this triangle, 0B and A, 0AB triangle, multiplied by 100, you get the same thing. Right? So basically, it is the area under the curve, Lorentz curve, compared with the area of the triangle. Because if it is perfect inequality, it goes like this and then 100. So you get the entire area covered, 0A to B triangle area. So that becomes same area divided by the total area is same, multiplied by 100. This you get 100. Otherwise, every time it get the value between 0 and 100. A Gini coefficient of 0 is complete income equality, while a Gini coefficient of 1 means complete income equal. 1 or 100 becomes, because earlier it says 100. So Gini coefficient is 1, but if you look at the so Gini coefficient goes from 0 to 100, or Gini actual coefficient should be 0 to 1. So you multiplied it by 100. That's how you get it. So if you look at this, you can see the Gini coefficient with area of the blue color divided by area of this triangle, 0AB triangle. Right. So that is the Gini coefficient. If you multiply it by 100, you get 0 to 100 scale. Generally, Gini coefficient is expressed as a fraction. Now, limitations of this Gini coefficient. So, by looking at the Gini coefficient, you don't know which quantile or which quintile you have the issue, because if you look at this Lorentz curve 1 and 2, right? Lorentz curve 1 and 2. So you have one curve, second curve, maybe Gini coefficient is more or less equal, but it has a two different distribution. So in this diagram, it has drawn the Gini coefficient for Lorentz curve 2 is lower than Gini coefficient for Lorentz curve 1. Okay, so 2 is smaller than 1. But the bottom 20 of the household obtains a smaller percentage of total income in the lower Gini coefficient case. So if you look at the thing, so in the lower 20%, you get a difference. So that means you can have a difference Lorentz curve or different Gini coefficient, but it does not describe about how it distributes. The curve can be totally different. So whether you can have a lower value at the beginning upfront and then in higher value at the end, or higher value upfront and then gradual decrease. You can have either way. Okay. So we learned 4 things now. First one, we learn how we look at a distribution of variable in a given area compared with the distribution of the base over that area. So if you take, for example, population of Sri Lanka, you have each district the population value. Okay, so you can calculate the percentage of population out of the total in each of the districts. Okay, then you have female population, right? Female population in each of these districts. You can calculate the percentage of female population. Then you can see the female population is uniformly distributed like the population. So you can get each district and put from the lowest to highest, rank it, and then draw the values. Right? The lowest to highest rank should be on the y-axis. So if you calculate the share, okay, say for example, Colombo population percentage out of the total country population is 9%. Okay, but the female population in Colombo is 5%. Right? So district 1, 9% versus 5%. Then you go to Gampaha. Cumulative population, Colombo 9, Gampaha 8, 17. So cumulative percentage is 17. Cumulative percentage of female population, Colombo it is 4, Gampaha it is 3, 7. Right? So you put 7. Likewise, you cumulate it over the all the regions and draw it. You don't need to do it in quintiles or quintiles, octiles. If you have 8, you don't need to do it. You can just do it by the each of the areas, each of the districts. Then you get the Lorentz curve, and the highest deviation which you observe is your Gini coefficient. Highest deviation that you observe is the Gini coefficient. So when you use ArcGIS or ArcGIS ArcPro, where you have the map of Sri Lanka with districts or DS divisions or whatever spatial divisions, when you have set of data, you can do the calculation in the attribute table and bring only the map values, final calculated values to the mapping purpose. So you can calculate the Gini coefficient. You can calculate the values, and then you can produce maps showing distribution of various parameters like this. So that is important. So what we are trying to do here is trying to understand how equal the distribution of resources, facilities, and the goods, how distribution of these variables are happening. So whether it is more or less equal to everybody, or whether one group or one area is getting most of the benefits while denying these benefits to the others. So you can understand that. Okay, any questions on this? Okay, if not, we'll move into the next topic, which is measures of central tendency. You have learned it in the basic statistics, mean, mode, and median. But when it comes to the spatial data, when it comes to a set of spatial data, which is identified by pair of XY coordinates, and see how central tendency measures can be calculated. Now, what is the center or middle or average of a point distribution? What is the center or the middle or the average of a point distribution? You have a set of points. Where is the middle point? Where is the center? So, where on the map is the center of a point distribution? So, we can calculate 5 things: mean center, weighted mean center, Manhattan median, Euclidean median, and weighted medians. We'll go into each one of these and see how we can calculate. All these are available now on ARC Pro or ArcGIS. These are available as measures. Now we will start with the mean center. It is same as the mean, same as the average. It is the center of gravity of a point distribution. If you have a number of points, what is the, if you put a pointer, how can you balance it? Only from the mean center, it's a center of gravity, you can balance the distribution of the point. So the definition, let xi and yi, I goes from 1 to n, be the coordinates of a given set of n points on the map. The mean center of this point distribution is defined as x bar, y bar, and given by summation of xi divided by n, and I goes from 1 to n, and y bar is summation of y values divided by n. Again, I goes from 1 to n. So it's very simple. It's like calculating 2 separate means. You calculate the x mean and you calculate the y mean. And that is the mean center. That is how you get the mean center. So it's all known things. You just get the average of x values. So if you have a series of coordinates, what you do is you get the x coordinate, get the average of x value, take the y values, get the average of y values. So you have the mean of x and mean of y. Okay. So if you go to the calculation example, we have few coordinates, and coordinates are 20, 40, 30, 60, 34, 52. Those are the coordinates. So if I write the coordinates here, we have first coordinate 20, 40. Second coordinate is 30, 60. Third coordinate is 34, 52. Next coordinate is 40, 40. And next one is 44, 42. And next one is 48, 62. Next one is 50, 10. Next one is 60, 50. Next one is last one is 90, 90. Right? This is the set of coordinates. So now what you do is we take the x value, average it, y value, we average it. So our mean center has the coordinate of 46.22 and 49.56. So this is our mean center coordinate. Okay, very simple. Right, okay. We go to the next slide. So it's simply the mean of x and y, also called center of gravity. If you want to calculate center of gravity, that is the same thing. Sum of differences between the mean x and all other x is 0, and same for the y. So when you calculate the mean, sum of all the difference between individual values versus the mean value of x is 0, because you have positive deviation and negative deviation. That is why when we calculate the standard deviation or variance, we square the differences. We don't take the differences as it is, we square it to remove the sign. So if it is minus, it becomes plus. If it is plus, still it becomes plus. Now where do you apply this mean center? Calculation of center of gravity of a population distribution is given by the mean center. The mean center of the population dot map is calculated for a series of maps of the same region at regular intervals of time. Right? So if you look at how people are, like for example, you look at the distribution of people on the map and calculate the average x and y. That is the how people are distributed around the country in terms of x and y coordinate. So then you get all these coordinates, average and get the mean center. And for example, if you take that for a particular year, you find the mean center of the population of the country. And after every 5 years, or when you look at it every 5 years, you calculate the mean center. Then what you will see with time, people are moving towards the western province. So you can see western, towards west, there's a movement of people. So there is a trend in the population. There's a trend to move towards the city, the capital. Similarly, if you look at the distribution, center of gravity of each ethnic group, take the population of Sinhalese people in all districts, calculate the mean center. and take the Tamil population, take the Muslim population, get the average. Or similarly, you can get the Buddhist average, Christians or Catholics, Muslims, Hindus, you can have, and then see with time how this center moves. How this center moves. So that shows, like, if the ethnic groups are moving aggregation, if they are moving together, live mixed in a way that is good, ethnic groups are mixing, having social mix, so that's good. Religions are also same. If the Hindu population is moving towards the north and the Catholic population moving towards the west, Buddhist population is moving towards the south, that doesn't look right. Okay? So that gives an idea of how the different trends are taking place. So it will be helpful for the policymakers to formulate policies based on these movements. So therefore, this mean center is very useful concept how we apply it. So once the calculation is very easy, but there may be very useful applications coming out of this. So it's just a summation of X and Y values, but it can give us insights into how a society behaves. Right? Similarly, you can do the calculation about the wildlife. You can do the calculation about the wildlife, whether they are moving towards some other area, whether they are just scattered, no movement, whether there is a significant trend showing they are moving away from the villages, they are moving into the forest. So you can see that. So this shows a mean center of population distribution pattern. So you can see it's moving. 1900, it was somewhere there. And with time, by year 2000, it has moved to a different place. So now the movement can be very fast. You can see that there are larger things, so you can see that it is moving very fast, not like before. So you can track changes in the distribution. So if you look at this text in the graph, it says mean center weighted by population over time. So you take each of these aerial units, get the population and calculate the mean center. So basically, it's not just XY, but the weighted value. You get the population as a weight. So you know how weighted values are calculated. So this is an example where we can use weighted value for. So how statistics, spatial statistics work? I borrowed it from a book on ArcGIS, Arc Toolbox, and the mean center equation is given. Weighted mean center, now we calculate, is given like this. So we can forget about the Z dimension. If you have any other dimension, we can get the weights as well. So if you go to the earlier version of this arc view, you can give the input as the point file, and then it calculates the mean center. You can also give weight field, weight also you can, so it will calculate the weighted average. Weighted mean center, which is associated with whatever the frequency, magnitude, or weight that you have for each point. So, for example, when the point distribution represents a city with a population, location of the mean center should be drawn towards those points with the largest population. So, you take the population as a variable out of the total. So, definition, let xi, yi is I is going to up to n be the coordinates of a given set of n points, and let wi be the weight attached to the ith point. The weighted mean center is given by this equation. So this is the weighted mean center calculation. If the population of the cities in the early example is 10, 20, 10, 20, 10, 80, 10, 90, and 100 respectively, you can calculate the weighted mean center for the same set of data. Okay, it's not a big deal. So this example where we calculate the population by weight and then get the x bar, the x w bar, and y sub w bar. Okay. So this is the more important part. The least square property of the arithmetic mean is valid for the mean center and weighted mean center. What does that mean? The arithmetic mean of a set of numbers minimizes x minus x bar squared. That means if you have a x bar calculated as the mean center, it minimizes the deviations or the difference between the mean and each observation. Right? So that is the general mean. But if you look at the equivalent property for the mean center, which is x bar y bar, which also minimizes xi minus x bar square plus yi minus y bar square. So if you take a data set, it minimizes x minus x bar squared, that is the square deviation. The summation of square deviation is minimum when you calculate the x bar as the mean center. So same property is valid for x bar y bar when we use your least square property, which is xi minus x bar squared, x deviation square, the squared x deviation plus squared y deviation is minimum when you calculate the weighted mean center. Your x deviation of the mean from each value of x and also the square deviation of each value from x minus mean plus the y minus y mean give you the least square property. Is it clear? Any doubts about it? So it is not multiplication xi minus x bar squared plus. So you add the least square property of x plus least square property of y. That, because if you take individually, this is the minimum at the mean center. Xi minus x bar squared is the minimum. Yi minus y bar squared minimum. If you take both, so these two is the minimum value. So if you look at the Pythagorean theorem, the distance between points x and yi and x bar y bar is given as the dxi minus x bar squared yi minus y bar squared square root of. Therefore, the mean center has the property that it minimizes the sum of square distances from itself to the n other points. So if you look at the simple Pythagorean theorem between 2 points, what you do is you take the x distance square plus y distance square and add these two together and get the square root of it. Right? So x distance is xy x1 minus x bar squared, x2 minus x bar squared up to xn minus x bar squared. Same with the y. So this satisfied the square distance. The mean center has the property that it minimizes the sum of square distances from itself to the n other points. But the problem with this is, like the mean center is also sensitive to the existence of extreme observations, extreme values. To see the sensitivity, if you assume 10 point as 1000 instead of 90, the mean center is now shifted to all outside the 9 points. Right? So it is sensitive to the extreme values. So some of the parameters, the value is measured how they respond to the extreme values. If they can respond well to the extreme values as well, that's a good estimation. But unfortunately, mean center and the weighted mean center, they are unable to be non-sensitive for the extreme observations. They are sensitive. Okay, moving to the next one. These are very basic things. We can move quickly. Median center. What is median center? It identifies the location that minimizes overall Euclidean distance to the feature in the data set. What does that mean? A location which minimizes overall Euclidean distance to the feature in the data set. Now, if you look at the mean center and the weighted mean center, right? If you look at mean center and the weighted mean center, which minimizes the x squared x distance plus squared y distance, right? So if you add squared x distance plus squared y distance together, it minimizes that when you add the mean center. But look at this median center, not the x distance and x squared distance and squared y distance. It minimizes overall Euclidean distance. What is Euclidean distance? Euclidean distance is the direct aerial distance between the 2 points. Aerial distance between the 2 points. Now, if you look at this, say you have a point here and a point here, right? And your distance is x distance is this and y distance is this. So what it minimizes is if you have set of points in the mean center, it minimizes the squared x distances plus squared y distances and summation of that. But here, what we have now is the Euclidean distance. We don't take it like this, we take Euclidean, aerial distance from here to there. So basically, what do you measure by the Pythagorean theorem rather than taking x and y separately? So median center identifies the location that minimizes overall Euclidean distance to the features in a dataset. So if you use ArcGIS, mean center tool gives you the point at the average x and average y coordinate for all feature centroids. The median center uses an iterative algorithm to find the point that minimizes Euclidean distance. So calculation of that is not very straightforward because it calculates, it's an iterative algorithm to calculate the minimum Euclidean distance. And not like mean center, median center is less influenced by the extreme distance values. Okay. We'll take a quick break and start in 5 minutes. Okay. Um, so if you look at the how median center works, I also got this copied from ArcGIS. The median center tool, because this explanation is there in the ArcGIS. The median center tool is a measure of central tendency that is robust to outliers. So the advantage of this median center compared with the mean center is sensitive to outliers. But median center is a robust measure to outliers. It identifies the location that minimizes travel from it to all other features in the dataset. So if you travel aerially, if you look at the Euclidean distance, it minimizes the distance from that point, median center, to all the points. If you take any other point, the distance is higher. For example, if you were to compute the mean center for a compact cluster of points, the results would be a location at the center of the cluster. If you then added a new point far away from the cluster and recomputed the mean center, you would notice that the result would be pulled towards the new outlier. If you were to perform the same experiment using the median center tool, however, you would see the new outlier has a much smaller impact on the overall result. The median center tool allows you to a specific weight field as well. You can think of weights as the number of trips associated with each feature. The weighted mean center is the location that minimizes distance for all trips. The method used to calculate the median center is an iterative procedure introduced by Kuhn and Kohn in 1962 and further outlined by Burt and Barber 1996. That is the textbook that I recommended, Burt and Barber. At each step, T in the algorithm, a candidate median center is found, xt, yt, and then refined until it represents the location that minimizes the Euclidean distance d to all features in the dataset. Now there's a point. While the median center tool returns a single point, there may be more than one location that would minimize the distance to all features. So it may not be a unique point. There may be few points which has the same characteristics. The calculation is xy minus xt squared plus yi minus yt squared square root of. So look at this example. What is the most central feature? If you look at the central feature as the Springfield, lowest total distance, but if you go by the weighted population, Baker is the central feature. Right? So that if you put a weight of the population, it becomes a different point now. So if you look at the ArcGIS tool, you put the input feature class, output feature class, distance method, you put the Euclidean distance. If you want, you can put a weight field. So then you can calculate the Euclidean or you can calculate the median center. Right. We'll go to the next one. Third one is a Manhattan median. So we look at the mean center, weighted mean center, median center. Now we look at Manhattan median. What is Manhattan? What is Manhattan? Anybody? We have a lot of surveys here in the class. So you should know what is meant by Manhattan. Anybody in the class? Can you all hear me?
Yes, sir.
Yeah.
Right.
Yes, sir.
Anybody who knows what is Manhattan? It was very commonly used sometime back on the TV news. It was coming up very regularly sometime back.
Sir. Hello? Sir.
Yes. Yes.
So it has measured from grid-based system.
Yes, exactly. Now the name Manhattan comes from, if you remember the 9/11 attack in the US, right? September 11th attack happened at the Twin Towers. In Twin Towers, this happened, right? Twin Towers, the attack was mainly focused on the Twin Towers. And that area is called Manhattan. Because the Manhattan means all the roads are going either in the north-south direction or east-west direction, like a grid, as you said. All the roads are going either north-south direction or east-west direction, forming a grid. Okay, that's why it's called Manhattan. So that's why this is also, when it is grid-like structure, we call it Manhattan. Manhattan median is application of median to point distribution. For example, earlier case, median center, we look at the Euclidean distance. From one point to another point, you can go aerially, straight line relationship, right? But now, this Manhattan median is your travel is restricted only to north-south and east-west directions, right? You can only move either east to west or west to east or north to south or south to north. Now, when you have a grid-like pattern, movement restriction, for a set of n observations, the median is the middle of n plus 1 divided by 2th observation in an ordered array of x. So if you have a set of x data, n observations of x, what it says is, it is an ordered array of x n plus 1 divided by, so if you have 21 points, your median is 21 plus 1 divided by 2th observation. That is 11th observation is. So we make it as XMYM, that is Manhattan. So XI minus XM absolute value plus YI minus YM absolute value, where travel is possible in north, south, or east, west directions. So it's the same thing, but here Xi minus Xm plus Yi minus Ym. So if you are given a set of data and ask you to calculate the mean center, median center, and then weighted mean center, weighted median center, and Manhattan median, you should be able to do it if you understand the concept. In the meantime, if you, more importantly, rather than giving a set of data and ask you to calculate, if I ask you, okay, you give me example of calculation of Manhattan distance in the real world. Take the example and see how you can calculate the Manhattan median for the real world data set. Right? So here in Manhattan median, your travel is restricted to north, south, or east, west. Therefore, Manhattan distance is always higher than the Euclidean distance, except it becomes equal when the 2 points lie either north, south, or east, west line. So if you take this example, n plus 1 divided by 2 observation, if it is n is an odd number, yes, you add 1, it becomes an even number, you can divide by 2. If it is an even number, say it is 15, 16, plus 1 divided by 2 is between 8 and 9. So it becomes an area between 8 and 9, right? So it can become a point when it is an odd number of points. When it is even number of points, it becomes an area. It is the point which minimizes the distance calculated by Pythagorean theorem from itself to n other points in a distribution. That is Euclidean median. Now we look at Euclidean median. Manhattan is only the distance in south and north direction. Euclidean median is the point which minimizes the distance by the Pythagorean theorem. So if you look at this Euclidean median, xt, yt are defined as the location that minimizes xi minus xt bar xt squared plus yi minus yt squared square root. So this is, now you learn few things. Median center, then Manhattan median, Euclidean median. So if you look at the median center, that location minimizes overall Euclidean distance to the features in a data set. Right? It minimizes the Euclidean distance to all the points in the data set. And when it comes to the Manhattan median, travel is possible north, south, or east, west direction, which is the Manhattan median and X value of Manhattan median from each data point plus Y value of which is minimum in this particular case. This one, the point which minimizes the distance calculated by Pythagorean theorem from itself to any other points on the distribution. And you can put the weighted Manhattan median, just put the weights, and also spatial median is a point of intersection of two perpendicular lines which divides equally in a north-south direction and east-west direction. Median is basically the middle value. So suppose you have 11 points. 11 points. If you order these 11 points from the lowest to highest, your sixth point, X value of the sixth point and Y value of the sixth point is the median value, spatial median value. Right? Now, although we discussed this, for you to understand it fully, you need to work out some examples. You need to have some experience from doing it. Okay? Therefore, I'll give you an exercise. Right? You don't need to do it for all the things, but we look at few things now. We look at mean center, median center, Manhattan, we look at the Manhattan median, Euclidean median, then we have weighted mean center, weighted median center, weighted Manhattan median, weighted Euclidean median. Right? We have 8. Each one of you, I'll give you a topic for each one of you. You take one topic and then think of a real world example. Don't put hypothetical example, think of a real world example. Just prepare 2 slides or 3 slides to explain this. What the mean center or median center, Euclidean mean center is. Right? If you see some problems with that, you can explain that also. So maximum like 3 to 4 slides, real world example, because it's easy for others to understand. Right? Now we have 31 in the class. So I will give you the topics for you to look at. Right? I just quickly go through I'll give you the topic 23055 mean center, 23064 median center, 23212 Manhattan median, 23213 Euclidean median, 23215 weighted mean center, 23226 weighted median center, 23229 weighted Manhattan median, 23237 weighted Euclidean median, 23239 mean center, 23305 median center, 24036 Manhattan median, 24080 Euclidean median, 24087 weighted mean center, 24095 weighted median center, 24136 weighted Manhattan median, 24161 mean center, 24163 median center, 24174 Manhattan median, 24194 Euclidean median, 24231 weighted mean center, 24077 weighted median center, 24030 weighted Manhattan median, and Dhammika Ratnayaka is weighted Euclidean median, 24079 mean center, 24043 median center is Lahiru Chaturanga Manhattan median, 24037 Euclidean median, 23219 weighted mean center, right? So I have given you, each one of you prepare 2 to 3 slides quickly so that we can understand the examples better, right? You don't need to send me, sorry?
Sir, I am Chintana Vesekar. I just rename my number, not mentioned.
Okay, so you can use weighted Manhattan median. Okay?
Okay, sir.
Right.
Sir,
So-
and 10 is 10. My one also not mentioned, sir.
Okay, then you can use weighted Euclidean median.
Okay, thank you, sir.
Right. So don't make presentations, huge presentation. Maximum 2, 3 or maximum 4 slides. Right? Just to show an real world example of how you can use this. Okay. Any questions? So we will do it next week. We'll spend about 1 hour just looking at your examples, right? So today is 2nd, 9th March 2024 from 10 to 11 we will have this presentation. I will give you some marks for this. Okay, and we will move into the next one now. Any questions? Right, we'll go into the measures of dispersion. So far, we have been looking at measures of central tendency. Now we will look at measures of dispersion. Now, mean center and central feature tools tell you about the center of distribution, but do not tell you about the overall distribution, how it works. Now, dispersion tool tell how dispersed our features are around that center. So we use basically like standard deviation in normal statistics, we use standard distance here, SD. Then we use directional distribution, for example, standard deviation, ellipse, and also we look at linear directional mean. But more commonly we use what is called standard distance. How dispersed the points are. If you look at the standard distance in terms of this measures distribution of features around the mean, right? Around the mean. So if you need to have the knowledge of the mean for this, because standard distance calculated is from this mean center. So if you see number of points, you can see for this number of points, what is the standard distance? And we see how we calculate it. If you go to ArcGIS, it will ask you input feature class, point features you can give, and then it will calculate the standard distance. So don't have to do anything, it will calculate the standard distance. And the underlying theoretical concept of this is standard distance is given by xi minus x bar squared divided by n plus yi minus y bar squared divided by n. So x bar and y bar are the coordinates of the mean center. So you need to have that knowledge of the mean center. So what you do is for each observation, you subtract from the mean, square it, and add it together. Every time you take the deviation from the mean, square it and sum it and divide by the number of observations. And then you do the same for y, and you add these two together and take the square root of it. Same equation you can extend if you have a weighted, if you want to calculate weighted standard distance. In addition to the first equation, what you have is Wi and then total Wi at the bottom. So it's not a big deal, it's very simple. You have the standard distance calculation. Xi minus x bar squared plus divide by n and yi minus y bar squared and sum and divide by n. Okay, if I give you a data set, right? If I give you a data set, can you calculate the standard distance, small data set? So my first coordinate is 5, 1, then 8, 4, 12, 8, 16, 10, and then 20, 12, 24, 16, 30, 18. Can you calculate the standard distance and give me the value very quickly? Do a quick calculation.